Happy Wednesday, everybody. This is Dr. Benton, and this is the second part of our global wind lecture. The first part, we talked about how the Coriolis effect affects wind, and now we're going to talk about the circulation cells that are created because of the Coriolis effect. So first, warm-up question, what is the Coriolis effect? And we have a meme of the day about wind. So just as a review, the Coriolis effect is that the wind appears to curve. It's not actually the wind that's curving, it's that the earth is rotating, the earth is spinning. So it moves out of the path of the wind. And remember, like if you're riding in a car and you see a tree, according to the tree, you're moving forward, but from the car's view, it looks like the car is moving backwards. It all depends on your frame of reference. We on the ground have the frame of reference that is being curved. And that's the Coriolis effect. Without the Coriolis effect, we would expect the air to go straight from the North Pole to the equator, or the South Pole to the equator. And that's because the North Pole is cold, the equator is warm. The North Pole has high pressure, the equator has low pressure. And wind will always blow from high pressure to low pressure. But it gets bent. So we don't just have one circulation cell connecting the high pressure to the low pressure. We actually have three, and that's because it only makes it about a third of the way down before it gets bent around. It only makes it a third of the way before it gets bent around. It only makes it about a third of the way before it gets bent around. So what we have is 1, 2, 3 circulation cells in each hemisphere. We call these global wind belts because they literally wrap around the earth like a belt. And they're kind of moving in different directions, right? Like this one's going down the way we would expect, but then this one's going up the way we wouldn't expect. And then this one's going down the way we would expect. And then here's the equator. Below the equator, it's going north to get to the equator. So they're all going in slightly different directions. We named these belts based on the direction the wind is blowing from. So, for example, up here, we call these easterlies because they're blowing to the east. The reason they're blowing to the east is because of that Coriolis effect. They move south, but they immediately bend to the right in the northern hemisphere, so they come from the northeast. Over the United States, we call these westerlies because they try to blow north, but they get bent to the right. They curve to the east. They come from the west, so we call those westerlies. Below us, these are the northeast trade winds, and those were named after the ancient trade routes when back in the days of sailing. People from England and Europe would sail to South America, would sail to the Caribbean Sea for trade, and the trade winds would be the ones to get them there. So we have these three different names for these three different global wind belts, and of course they repeat themselves in the southern hemisphere. And they're pretty evenly divided, 0, 30, 60, 90. 0 degrees latitude is the equator, 90 degrees latitude is the pole. 90 degrees north is the North Pole, 90 degrees south is the South Pole. And every 30, it changes. So you'll also hear me refer to these by their climate zones. This is a tropical region, tropical trade winds. This is a temperate region where we live in the westerlies. And then easterlies up here are polar because they're near the poles. So interesting thing about these global winds, we call these the prevailing winds in a region. Well, let's say that I'm actually flying east to west or west to east. So say from Paris to New York and back. If I was flying from Paris, flying west to New York, it would take 8 hours and 35 minutes. But on the return trip, flying from New York to Paris, it only takes 7 hours and 25 minutes. Can anybody guess why that is? It takes an hour longer to fly from Paris to New York than it does from New York to Paris. And the reason is because of the westerly winds, those prevailing westerlies. The westerlies are always blowing from the west, so if you're flying to Paris, they actually help push you along. You get to France faster. And that's what we saw here, right? You get to France faster. But if we're going back, we're flying against the easterlies. We're flying against it, trying to go from France to New York. We're going to fly slower. So pilots try to take advantage of this return trip speed Same thing with jet streams that we're going to talk about in a second. So within each circulation cell, we expect the wind to be going north and south, but what we actually see on the surface is east to west, and that's because of the Coriolis effect. And the Coriolis effect, remember, is dictated by latitude because the Earth has different speeds of rotation at different latitudes. It's faster at the equator, it's slower at the poles. So as we go down, the Earth is getting faster and faster. That makes the wind appear slower and slower, so it kind of falls behind the rotation. If I'm going in the opposite direction, I'm going from fast to slow. The Earth is actually getting slower, but we see that as the wind getting faster, the same way the trees go backwards when we're going forwards. And these changes happen about every 30 degrees latitude. What this also means, though, is that there's areas where the wind is blowing away from. It's actually blowing away from this 30. The wind is actually blowing towards, converging at this 60-degree Arctic Circle. So what we have are not just high and low pressure areas at the equator and the poles, we also have high and low pressure latitudes in between. High pressure at the pole because it's cold, and that's what we would expect. Low pressure at the equator because it's warm, and that's what we would expect. But here, the wind is converging. It's actually pushing together, and when it does, it rises. It floats up to circulate back. We call this advection. It completes the convection-advection current. So since this air is rising, it actually is like low pressure. It's like a vacuum. Well, here's the opposite. The winds are kind of pushing down and away from each other. The winds are coming down and away, down and away. So that downward pressing wind is actually like high pressure. So the places where it's coming down and diverging are high pressure. The places where it's going up to spread are low pressure. So we have low pressure at the equator, high pressure at the poles, but then we also have a high pressure here at 30 degrees and low pressure here at 60 degrees. And in this case, it doesn't have much to do with the temperature. It has to do with the direction of this circulation. Here, the air is coming down to create that high pressure. Here, the air is going up to create that low pressure. We have special names for these latitudes. This subtropical high pressure system we also call the horse latitudes. Let's see, I think there's a picture that shows it. They call it the horse latitudes because here in between these two pressure systems the wind kind of stops. Back when they were sailing from Europe to the Americas, they would bring horses with them, but if their ship got stalled, they might run out of food and water to feed the horses. So they would either, the horses would die and they would dump them overboard, or they would eat the horses so that they would have food for themselves. So kind of morbid, but that's where it gets the name, is people would dump their horses overboard at the horse latitudes. Down here we have the doldrums, and you might have heard that word before if you're very literate. We think of doldrums as kind of like depressing, sad, and that's true here too because there's not much wind in between the circulation cells. It's going up down, not side side. In this case, since it's going up, it creates a lot of stormy weather like clouds, and we're going to learn more about how the pressure systems affect weather in the next standard. But you might hear these referred to as the doldrums, you might hear these referred to as the horse latitudes. You really don't need to know these for your test though. In class, we would be making these diagrams. We would be labeling these diagrams. We would be trying to appreciate how all the parts fit together. Here for distance learning, I just want you to appreciate the principles behind it. Why is the air moving in the direction it's moving? It's moving from the poles to the equator because it's moving from high pressure to low pressure. Why is the air circulating? Because of the Coriolis effect. It tries to go in a certain direction, but then it gets bent so much that it has to curve back. It actually curves up where the air systems meet. Now here, this one's actually kind of flowing backwards. Do you see that? We would expect it to be going towards the equator and then kind of bending to the right. But here it's going opposite. The westerlies are going opposite because it's getting rolled between the other two, kind of like a gear. If we say that over here is the North Pole where we have high pressure, and over here is the equator where we have low pressure, the air tries to flow, right? But as it tries to flow, it actually gets bent to the side. As it tries to flow, it actually gets bent to the side. Same thing here. As it tries to flow, it gets bent to the side. It gets bent to the side. Well, here in the middle, it's doing the same thing, but since these two are rolling in the correct direction from the poles to the equator, and the northern hemisphere curving to the right each time, this one has to go into the opposite direction to compensate. That's the way gears work together. That's the way these wind belts work together. So this middle cell, this temperate cell, they have a proper name, Ferrel cell, it flows in the opposite direction. The polar cell is rolling this way, the Ferrel cell is rolling that way. And since the Ferrel cell is rolling that way, it allows the Hadley cell, it allows the Hadley cell to move this direction. So the only thing I would really memorize, name-wise, is the westerlies, because that's where we live. We've kind of already learned about polar being up north. We've already kind of learned about tropical being near the equator. In this temperate zone, we have the westerly prevailing winds, and it is important for pilots, for air travel, for flight. One last thing. We talked about where they meet, where the gears meet. The air is going up, or the air is sinking down. We have low pressure going up. We have high pressure going down. What that actually creates is jet streams. Here, where they're rising and diverging, we have a polar jet stream. And it tends to be very powerful. Here, where they're coming together and sinking, we have a subtropical jet stream at this 30-degree latitude. The subtropical jet stream, a little less strong. These are both very fast. The wind speeds here are like rivers of air. Rivers of air in an ocean of air, the same way ocean currents are. So these are like air currents in the atmosphere, the same way ocean currents float through the water. But in this case, if the air is usually blowing, 10 degrees, miles per hour, 10 miles per hour, 20 miles per hour, these are like hundreds, like over 200 miles per hour, like faster than a tornado. So we talked about how pilots can take advantage of these westerly winds, and you can kind of see how the winds over the United States are blowing from the west. If they can actually fly in or near that jet stream, they get propelled really fast. So they get to save a lot of fuel, and they get to their destination faster. The problem, like you can see in this picture, though, is that they're kind of moving, they're bending, they're not staying in a perfect shape, they're twisting, they're meandering. So what that means is that these belts are constantly changing position. If the polar belt goes a little low, it brings this cold air a little lower into the United States. So it really dictates a lot of the winter weather we see in the Midwest, and in the north, like the northeast, New England. So jet streams, fast-moving currents of air high in the atmosphere, like miles above the ground. So final question, ticket out the door. What is a circulation cell? Good. And hopefully we've learned what a circulation cell is now. A circulation cell is the way the global winds move. The global winds move because of both temperature differences and the Coriolis effect. It's the temperature differences that drive the overall movement of air from the poles to the equator. But because of the Coriolis effect, it makes three different cells, three different circulation areas, three different convection areas between each pole and the equator. And to end with another inspirational quote, this one's from Winston Churchill. He was the prime minister, kind of like the president of England during World War II. He was a mediocre statesman until the war, and then he really shined, and so he's got a lot of memorable quotes. Success is not final. Failure is not fatal. It's the courage to continue that counts. And what he means is that all because you're ahead doesn't mean you're always going to be ahead, and all because you're behind doesn't mean you're always going to be behind. You've got to keep going. You can't let yourself give up. So thank you for watching. Thank you for joining me today.